Hello, so today we are looking at the theoretical part of the band gap of germanium experiment. In this particular section, we will look at how we will find our band gap. And then our band gap is also known as the energy gap of germanium. Okay, so look at how to find the energy gap of germanium. So for the part 1 of the video, we looked at how the experiment is performed. Now, after you've taken your values, right, the table should look something like this. Okay, first of all, we were given a current of 5 milliampere, right? So a current of 5 milliampere. Now, the cross-sectional area and the length of the germanium specimen is already given, right? They were already given in the book. So all these are things that were already given in the manual. Okay, so after getting this, we need to draw the table. Now we know how to get our values. We started from room temperature, right, to 170 degrees. Now the first column is about the temperature in degrees Celsius. The second column, we need to convert everything here into Kelvin. Okay, so the second column is the temperature in Kelvin. Okay, so we convert everything here into Kelvin. Then the third column, we find the inverse or the reciprocal of the temperature in Kelvin. Then we write the values here. So 1 over the answer here, we write it here. 1 over the answer here, we write it here. So that will be this column. Now this column is the voltage that we got on the multimeter. If you remember the first video, the part 1, the voltage that we got on the multimeter, that will be in this column. Now for this column, we'll find the conductivity for every respective temperature. We'll find the conductivity here in this column. Okay, and then this column, we find the ln of the conductivity here. So on the calculator, you see ln, right, In. Then the conductivity, so you press that one on the calculator, then you add this value, you write the answer here. So that's how the table will look like. Okay, now let's go to where we plot the graph. So let's look at how the graph will be like. So on this part, right, on this part, we are expecting to have two graphs, right? Now, if you remember the table, we have voltage here, we have 1 over the Kelvin here, right? 1 over the temperature in Kelvin here, we have ln here, okay? We have temperature here. So in using this, we realize that our first graph, we are expecting two graphs. One that is a curve, right? A positive graph, which is a curve. Now, we'll be plotting voltage on the ordinate, and then we plot the temperature on the abscissa, right? Okay. Then the second graph, we'll be plotting the ln on the ordinate. So it has a ln, negative ln values, right here. So this side is negative, and then we have a positive abscissa values here, which is the 1 over the Kelvin, right? So 1 over Kelvin. Let me put prime here so that you know that this temperature is in Kelvin. Okay, so if you check the unit here, it's 1 over Kelvin. Okay, so we plot the ln, which is the last column on the table, against this, and we have a straight line like this. Okay, now after that, we come and make use of this equation, right, to find the energy gap, right? So this is how we find the energy gap, this equation. Now before that, I would tell you how we came about this equation. You see, we'll try and prove how we came about this equation. Okay, so for the first graph, we find our slope. Okay, we find our slope on the first graph. Okay, then we can write our slope answer. So that's what I did here. I've not plotted, I've not found the slope. Okay, this is just a sketch to demonstrate, okay, how it works. So for the first graph, we find our slope, right? Now we can just find the percentage error of the slope. Okay, now this formula here is the conductivity, right? This one, we all know that conductivity is also the same as 1 over, or the inverse of resistivity. So this particular value here is resistivity. In some of my other videos, I spoke about it. I think the Wheatstone bridge experiment, I spoke about conductivity and then resistivity. Okay, so anytime you have cross-sectional area, you have voltage, current, and length, you are expected to find conductivity or resistivity. So the inverse of resistivity will give you conductivity in that order. Okay, so that's what we have here, conductivity sign, and then 1 over is the same as 1 over resistivity, right? This is resistivity, which is the same as the length times the current over the area times the volume. Okay, the length, current, area, and volume. Okay, so we realize that when we come back here, we have length, area, current, and then the voltage. Okay, so this one is voltage, this is voltage. Now let's look at how we came about this experiment. So this is what we are finding. We are interested in finding the energy gap of the germanium specimen, right, in the first video. Now what we do next is that we have this equation, right? There is this equation that was written in the manual. Okay, this equation. Now the main thing is that if we are supposed to plot, right, we are plotting lean, right, this against this. What we have to do is that now let's try and rewrite this. Okay, now that will be lean, and then the conductivity sign, this the conductivity sign equals to 1 over lane conductivity sign naught minus the band gap, which is the energy gap. Okay, the band gap over 2k, 2, and then the temperature. Now this equation is what we are making use of. Okay, so this was is given in the manual. Now it's very clear here, we are not deriving or deducing anything. We are just trying to deduce this, how to get the energy gap. Now this formula tells us that to get the energy gap, we need to negate the slope that we'll get in this graph, right? We negate the slope that we get in this particular graph, this graph, the slope that we get, which is a negative, times 2 and then k. The k is our Boltzmann's constant, so that's the value for our Boltzmann's constant, so 2k, right? So to get the energy gap, the slope that you get in your graph, multiply it by 2 times Boltzmann's constant. Now we want to know how this equation came about, so that's what we are trying to do here. Now realize that we are plotting this against this. Okay, against this against this. It means that realize this on the y-axis, this on the x-axis. So if you follow the other videos very well, you realize that if this is our y, and then we are supposed to arrange this to look like y equals to mx plus c, what we have to do is this lane conductivity, please, this is not 6, conductivity sign, okay, and then lane of conductivity naught, okay, minus eg 2k dot 1 over t. So you see this, if we are supposed to factorize out this t, we will have something like this equation. Now to arrange this, we can say that this lane, this equals to, now we can bring the whole of this in front here, okay, so that it looks like mx, because this is our x. Realize that this is our y, this is our x, this everything here is our m, and then our plus c is the whole of this. So what we can do is we bring this here, eg 2k dot 1 over t, right, plus the lane of conductivity naught. Okay, now to arrange this to look like this, that's what we've done here. Okay, now we can now see that our y component is now lane of conductivity, our x component is 1 over t, our m, which is our gradient, you see this is our gradient, our m, you see this is the equation of a straight line, this x component, this y, this is the intercept, and then this is our slope, right? So our slope or our gradient equals to negative eg over 2k, and then our c, which is our intercept, is the lane of conductivity naught. Okay, like this. Now, after finding your slope here, right? After finding your slope here, okay, now I have to come and equate the slope to negative Eg on 2k, right? We are interested in finding the band gap, and I said earlier on that the band gap is the same as the energy gap. Okay, now to find this, let me write here. Now to find the energy gap, we have to make Eg the subject, where we will get Eg equals to minus m times 2k. Okay, so that's how come we got this expression here. Okay, if you are supposed to make Eg the subject here, so after equating our slope to this, because we said anything in front of our x component is our gradient or our slope. Now, if you are supposed to equate our slope to this particular equation, we'll have, and then we make our Eg the subject, because we are interested in finding Eg. We are interested in finding Eg. So we equate our slope here. So now we know this, which is the value of our slope from the graph. We don't know this, which we are interested in finding. We know this is Boltzmann's constant, and there's another constant too. So we can just make Eg the subject like this, and then we can find the energy gap. So that's how we find the band gap of germanium using this particular method. Okay, so that's what I wrote here, right? That's what I did here. Now, the theoretical value, you can find the percentage error, as I said earlier on. Your theoretical value is 0.6 electron volts. Okay, 0.6 electron volt, right? So you can find the experimental one, and then you can find the percentage error from the work as well. I mean, finding the error, percentage error in the work. Okay, so that's how we find the energy gap of germanium. If you have any questions, feel free to leave your comments under the video. Thank you.